Alright, boys and girls, welcome to our first video lesson in Chapter 3. 3-1, Exponential Functions. Alright, boys and girls, you may recall these rules of exponents from our Algebra 1 and Algebra 2. They are some very important things that we're going to be basing a lot of what we're going to be doing this chapter on in this chapter. Most important are some of these that when you when you multiply exponents, a to the x times a to the y is a to the x plus y. You add the exponents. When you divide exponents, a to the x divided by a to the y is a to the x minus y. When we raise an exponent to a power, we multiply the exponents. A to the x raised to the y is a to the x times y. Okay, this is raising a product to a power. This is raising a quotient to a power. Also important, a to the 0 is equal to 1. Anything to the 0 power is 1. Anything to the first power is itself, so a to the 1 is a. And anything to the negative 1 power is the reciprocal, 1 over a. Don't forget that 1 over x is always equal to 1. And if a to the x is equal to a to the y, then x is equal to the y, and we call this the exponential property of equality. Okay, take a couple of quick seconds to write down your powers. I don't suggest that you sit down and study these, but I certainly suggest that you familiarize yourself with these different powers. These in red right here are the powers of 2. These are the powers of 2, so 2 to the 0 power is 1. 2 to the 1 power is 2, 2 to the second is 4, 2 to the third is 8, etc. All the way on down to 2 to the 10 power is 1024. In blue, these are our powers of 3. 3 to the 0 is 1, 3 to the 1 is 3. 3 to the second, of course, is 9. 3 to the third is 27. And we go all the way down to 3 to the 6 is 729. These in purple are our powers of 4. 4 to the 0 is 1, 4 to the 1 is 4, 4 squared is 16, 4 to the third, of course, is 64, etc. Right down to 4 to the fifth is 24. And in green here, these are our powers of 5. 5 to the 0 is 1, 5 to the first, 5 to the second is 25, etc. Right down to 5 to the fifth, 3125. Make sure you get these down into your notes and familiarize yourself with these numbers so when you see them, you recognize them as powers. Okay, this is a lot of the same chart right here, but these are just our squares and our cubes. Okay, in blue we have all of our squares up until 20 squared. 20 squared, of course, is 400. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, etc. In red here, these are our cubes. So we have our cubes all the way to 10 to the third. 10 to the third is 1,000. Okay. Again, I don't want you to go home and study these, but I do want you to familiarize yourself with them. You should know most of them anyway. So when you see them, you say, "Oh, I think that's something to the third power." Or if we see 289, you know, "Oh yeah, that's 17 squared." Okay. Make sure you get these down. Okay, we're going to work with one of our first exponential functions, y equals 2 to the x. Don't forget there are 3 ways to describe a function. One of them, of course, is the equation. This is y equals 2 to the x, and this is an exponential function because our x is an exponent. It's actually in an exponent. It's 2 to the x power. So we're going to make a quick table. X equals 0. If x equals 0, y equals 2 to the 0. 2 to the 0, of course, is 1. Then we're going to do y equals 2 to the first. Y equals 2 to the first is 2. Then we're going to do y equals 2 to the second. That's 4. Y equals 2 to the third is 8. When we do when we let x equal negative 1, we're going to have y equals 2 to the negative 1, which is y equals 1 over 2 to the first, which of course is 1/2. y equals 2 to the neg 2 means x is neg 2, so y equals 2 to the neg 2 is 1 over 2 squared, which is 1 over 4. These are just the reciprocals of what we see above, and 2 to the negative 3 is 1 over 8. When I go ahead and make a graph, our third way to describe a function is to picture the graph. I'm going to plot my points. I'll do that in blue. When x equals 0, y is 1. So I have a y-intercept right here at 1. Now when x is 1, y is 2, so that's here. When x is 2, y is 4, that's up here. When x is 3, y is 8, that's going to be up here. When x is neg 1, y is 1/2, that's here. Doing my best here with my marshmallow. And then we get when y is neg 2, or x is neg 2, y is 1/4. And when x is neg 3, y is 1/8. That's going to be down here somewhere. What happens with an exponential function? We hug the x-axis to the left. We pass through the y-intercept of 1, so 0, 1, 1, 2, 2, 4, 3, 8, etc. The next one would be 4, 16. Our exponential functions then shoot up to the right very quickly. So our exponential function is asymptotic on the left. In other words, it's going to hug the x-axis on the negative side, and it shoots up to the right very largely on the positive x side of our graph. Okay, let's look at a second function here, y equals 10 to the x. So we're going to replace x or we're going to make some ordered pairs. Let x be 0, 1, 2, 3, neg 1, neg 2, neg 3. So for x equals 0, that's y equals 10 to the 0, or y equals 1. For x is 1, that would be y equals 10 to the first, so that would be 10. For x is 2, y would be 10 to the second, which is 10 times 10, or 100. When x is 3, y would be 10 to the third, which is 10 times 10 times 10, or 1,000. When x is negative 1, it's the reciprocal of y of when x is positive 1, so it would be 1/10, or 0.1. When x is neg 2, that's 10 to the negative 2 power, which is 1 over 100, or 1/100th, or 0.01. And when x is neg 3, y equals 1/1000th, which is 1 over 10 to the third, or 0.001. When we plot these points, you're going to see once again, my y-intercept is 1. So when x is 0, y is 1. That's right here. If x is 1, y is 10. Up here. When x is 2, y is 100. When x is 3, y is 1,000. It's already off the page. So we're going to shoot this thing up here like this. It gets big very, very, very quick. But again, our function moves forever to the right. On the left-hand side, when x is neg 1, we're at 1/10. When x is neg 2, we're at 1/100th. When x is neg 3, we're at 1/1000th. So you can see we hug the x-axis. We never quite get there, but it's asymptotic to the x-axis. Goes through the point 0, 1, and shoots up to the right very, very quickly as it moves to the right. But once again, our domain is all real numbers, and our range is all positive numbers. So let's just look at again an exponential function real quick. We know that we have a y-intercept of 0, 1. I'm going to draw it in the best I can here in red. An exponential function, no matter what its base, is going to get larger to the right, generally speaking, and shoot up relatively quick. To the left, we're going to eventually, or very quickly, approach the x-axis. It's going to be asymptotic to the x-axis on the left-hand side. Just so you know, and we will explain why in class, b can never be 0. B can never be 0. Because if b is 0, we would have 0 to a power, which is just 0, not a very exciting graph. B can also not be 1, because then we would have 1 to any power, so that would also just be, y would always be 1, so that doesn't work either. B cannot be a negative, and I'll explain why in class, but b cannot be a negative, so all three of those things for b, b cannot be 0, 1, or neg. If b is a fraction, something interesting happens here. This is fine if b is a fraction. But what happens now is our curve is going to be reflected over the x-axis. So it's going to be asymptotic on the right. It's going to shoot off and get large as we move to the left, and we'll explain why that happens in class as well. But looking at either exponential function, we can see now that the domain, this graph does move forever to both left and right. So the domain is all real numbers. And the range, the graph will never go below the x-axis, and in fact will never reach the x-axis. It's asymptotic to the x-axis, so the range is all positive numbers, or in other words, y is greater than 0. It's not equal to 0. It's not less than 0, but the range is all positive numbers. Okay, folks, we're going to talk about graphing and what happens when we have our constants a, b, h, and k. Okay, you already know this. Okay, a right here in trig, this is we call our amplitude, but this is once again our vertical stretch. If a is a number bigger than 1, or it's a compression if a is a fraction between 0 and 1. If a is negative, of course, we know that our graph is flipped over the x-axis. It's flipped over the x-axis. Okay, the b here is not the b that is the horizontal squish, but the b right here is the base of our exponent. Okay, it is our rate of growth. The bigger the b is, our graph will get bigger faster. However, as we just said, if b is a fraction, it is reflected, our graph is reflected over the y-axis. Please remember that b, and I'll write this down again for you, b cannot equal 0, 1, or a negative. Okay? Just like in trig, our h is our horizontal shift. In trig, we call it our phase shift, but this is our horizontal shift. And in our k, we call it a climb. It's our vertical shift. It's our vertical shift, and it determines the horizontal asymptote. Our critical point, which is 0, 1, is always going to be h, k plus a. H, k plus a. Okay, why don't you guys spend a quick couple of minutes here then. Okay, we're going to try to match up these graphs right here, or the graphs right here, with these equations right here. There are 5 graphs, A, B, C, D, and E. You match them up with the equations 1, 2, 3, 4, and 5. Note, functions not necessarily drawn to scale. Do your best with these. They're not drawn to scale, but they are drawn to scale in reference to one another. Stop the tape and see if you can match these guys up. Okay, the first two, y equals 2 to the x and y equals 10 to the x, these are just our basic exponential functions. So they are either going to be b or d. They both pass through the ordered pair 0, 1. They have a y-intercept of 1. B gets bigger faster than d, so therefore b would be y equals 10 to the x, and d would be y equals 2 to the x, because it doesn't get big quite as fast as b. Number 3, y equals 2 to the x plus 2 is just like graph B, but the whole graph just moved up 2, so it would be graph C. Number 4, y equals 2 to the neg x minus 3. This graph just gets reflected, and it gets reflected, over the y-axis, so it is a mirror image over the y-axis, and it also has a climb of negative 3, so it goes down 3. So that would be this one right here at A. And the last one, we have an A of negative 1, so the graph is upside down. It also has a climb of 3, so it went up 3. It's an upside down exponential graph that also climbed 3, so it's at E. Okay, let's draw some quick graphs using our transformations. Let's start with this first one here. G of x is equal to 5 to the x power. It's an exponential function because our exponent is x. X is actually in the exponent. It's not x to the fifth. It's 5 to the x power. So it's an exponential function. Our a, in this case, is going to be 1. There is an imaginary 1 in front of the whole thing here. So this is like 1 times 5 to the x. Okay. Our b here is 5. As we can see, our base is 5. Our h, well, there is nothing in the exponent. Our h is going to be 0. And there's nothing being added to the expression. So k is 0. So when I go to graph this guy, I have an ordered pair of 0, 1. It's going to shoot up to the right, so 1 to the 5th, or 5 to the 1 power is 5, so it's going to get big relatively quickly. Shoots off to the right, gets big, very large, and to the left, we're going to relatively quickly start to hug the x-axis. So it's asymptotic on the x-axis. Notice, though, again, our domain is going to be all real numbers. And the range is only greater than, but not equal to, 0. So y is greater than 0. And there is our range. All right, you guys try this one for a minute. Just fill in the a, the b, the h, and the k. Fill those in, and then we'll draw the graph together. Are you filling them in? I'm waiting for you. Okay, you should have found that a is 1. There's an imaginary 1 right in front of this whole thing right here. So a is 1. It's 1 times 3 halves to the x plus 2 power. B, of course, is 3 halves. B is a fraction in this case, but it's a fraction larger than 1, so it's still going to shoot off to the right. As we move to the right, it's going to get larger, and as we move to the left, it's going to become asymptotic to the x-axis. It's just going to do so more gradually because it's a smaller number than, say, 2 or 5 or 10. Our h is negative 2. Again, very good. Notice that it's negative 2. When it looks positive, it's actually a negative 2 there. It's x minus h. And our k is 0. We actually have a plus 0 here to the right. Okay? As we go ahead and graph this now, if I had just y equals 3 halves to the x without a shift, I would have a y-intercept at 0, 1. But what's going to happen now with that y-intercept is going to go 2 places to the left. So I have a critical point at negative 2, 1. Our graph is going to be an exponential graph now. It's going to shoot off to the right, but not as fast as some of the others because our b is 3 halves. And then it's going to be asymptotic on the left-hand side, but take a little bit longer to get down there because we have, again, a smaller b. There is no climb, so there's our picture. All right, you guys fill in here. What do we have for our A, our B, our H, and our K? Okay, stop the tape and fill these in real quick. All right, let's fill these ones in. A, of course, here is, that's right, you got it, negative 2. Our B, you're saying 5, be careful, it's actually not a 5. We have a negative x there, and I haven't gone over that in the video yet, but we'll go over that in class. What that really means is, because it's a negative exponent, it's the reciprocal. Our B here is actually 1/5, or the reciprocal of 5. Our H is 0. You can see there is nothing inside there with the x, so our H is 0. And our K is, you got it, negative 3. So we're going to have a climb over it. The whole graph is going to shift down 3 places. Okay, so let's start here with our critical point. Our critical point typically would be at 0, 1, which would be, I'm going to get it in yellow, right here. But instead now it's going to be upside down. And it's going to be stretched by a factor of 2, so it's actually going to be here at negative 2, 0, negative 2, and then it needs to move down 3 more places, down here to 0, negative 5. There's going to be our critical point, our exponential function. Our exponential function typically shoots off to the right, but this time because we have a fractional b, it shoots off to the left, and it's upside down, so it's actually going to go something like this, shoot down like that. Typically it'd be shooting up like this, but now we have a mirror image both ways due to the fractional b and the negative a. It's then going to hug the asymptote to the right to the positive side, and our asymptote now is going to be at at -3 because k was -3, and there is our picture. Okay, a couple more things. Just make sure you have these in your notes. Exponential growth and decay. This is our compound growth formula, and we're going to go over this in class and why this makes perfect sense. A equals p times 1 plus r to the n raised to the nt. And here's a second formula, which is going to make your life easier if you learn this formula. A equals p to the 1/2 over, A equals p times 1/2 raised to the t over h power, where h is our half-life. And also just take a couple minutes right here, make sure this is into your notes. We'll talk about this in class, but here's our compound interest formula. Our P is our starting amount of money, or the principal, the starting amount of anything. R is our annual rate, written as a decimal. T is time in years. A is the amount of money, or the amount of growth we have at the end. And the N is the number of payments per year, or the number of times that things are growing. And we are measuring that growth per year. That's it, folks. We'll spend a lot more time in exponential functions when we get back to school. We'll see you then. Have a great time. Bye.